Oh, good afternoon, everyone. This is episode 66 of Codebase Alpha, and it's another quite momentous stream for me because I'm actually now wearing my Live Coders team jersey, which arrived in the post just the other day. So yeah, this is our team journey for the Live Coders team. As you can see, it's quite nice. It's got our logo on the front with Live Coders. It's got our sponsors. It's very difficult to point here, so it's it's over here. Oh, I can't get it. It's got our sponsors logo here, which is contentlab.io. So they're sponsoring the jerseys this year. Hopefully, we'll get different sponsors going forward. And it's got my team name on the back, which is obviously Codebase Alpha. So it's really nice. It's really comfortable. So I'm wearing it for the first time. So hopefully I shall remember to wear this on every stream going forward, assuming it's not in the wash. Okay, so this is part of our kind of midweek series of streams, and normally during this time I might look at something like the bot and look at the text adventure which we're working on, and that will be coming back. It's not gone away. I think we're still working on that. There's still lots of stuff I want to do since the last time we worked on it on stream. It's not something I tend to work on off stream that much because it's really quite interesting for people to see it kind of grow and build. But what I'd like to do today is introduce a new project which I've started working on. And I've kind of called it Project Z, or Z if you're in the US. So this is the emulation of the Z80 chip and CPU chip in C#. So this kind of project came about because of two things really. There was something kind of nagging away at me to do something like this when Brendan over at Dev Chatter was working on Interactive 7, which is his project for chat being able to interact with Final Fantasy 7 as a game. And there's a lot of kind of memory manipulation going on there, and that's all kind of quite intriguing, especially kind of as I've worked in the past with what we used to call microprocessors, primitive personal computers back in the day. And I used to program the 6502 chip in assembly language, and lo and behold, one of my favourite streamers is Javid X9, who is a C++ programmer, and it does some absolutely fantastic streams and really excellent YouTube series of videos as well. He started working on the emulation of Nintendo Entertainment System, which is a 6502 driven system. And I've been watching his series of YouTube videos, and it's absolutely fascinating stuff. And then I found this book. I don't know if you can see it. This is the Z80 reference guide. This was lying around in a cupboard upstairs, and I thought, you know what? I think I should try and emulate the Z80. It's quite a thick book. Rambling Geek, thank you for the subscription. Thank you so much. That's very, very kind of you. Let's get some alpha actually for that. So we've got our alpha. We can't see that on this thing, so let's just pop over to the coding. There we go. There's our hyperspatial hype for Rambling Geek. So thank you very much for that subscription. As I was saying, we found this, yes, fancy jersey, yes, it's great, isn't it? So I found this book, Z80 reference book, and I thought, well, maybe I could have a go at coding the Z80 chip. And the kind of initial plan, I'm not aiming to build an emulator for a game system, though that could happen in the future. The idea initially of the project is to produce a good emulation of the Z80 chip and to provide it as a NuGet package so that other people can use it. And we will then possibly continue, maybe we'll emulate a system that can use the CP/M operating system, which is what we used to use when we had Z80 processors in our computers. We could even go on to things like ZX Spectrum emulation if we wanted to get into the games area, which is not something that I don't play games that much, only kind of tabletop games rather than computer games. Yeah, so the clue really how to get going on this was provided by the videos of Javid X9, also known as One Lone Coder on YouTube, so do check him out. Actually, I'll put a shout out in chat. Javid X9. So Rambling Geek, you've got your team coders welcome there. Look at that, actually worked. So that's the first time I've actually tried it with somebody else other than myself. So I'm glad that worked. So yes, do check out Rambling Geek's stream as well. So he's a great chill streamer. So I was saying that he gave me the clues where to start really, and it's quite logical. We're just going to build a class, so it's just a matter of doing that. Now the 6502 chip which he is emulating has about 59 instructions. The Z80 has many more. In fact, some of the later iterations of the Z80 kind of architecture, such as the Z280 and the Z380, had over 2,000 instructions. And I'm not proposing to emulate one of those, but the Z80's got enough. It's got hundreds of instructions, and some of them are quite interesting, and we might as well see what we can do with it. So let's go and have a look at the project. So here we are. So yes, so how do we start with this kind of project? Well, you see, what we've got over here is in our solution, we've got a Z80 class, and I've created that as a partial class. I don't know if you know about this in C#. You can have these partial classes, which mean you can have a class which spans multiple files. We've got the other parts of the partial class are Z80.instructions, which is going to contain all of the code which actually does the various CPU instructions, and Z80 address modes, which is the addressing modes. So we'll come across what we mean by addressing modes shortly. There's the instructions, and we've got a couple of instructions coded up already. Okay, but Z80 is the main class. There's another class here called instruction, which basically is it defines information about each operation code that we're going to be using, and we've also got an interface called iBus, and I'll quickly explain what that is. Yes, Rambling Geek, they are very good. So you can use it to extend classes. So if I provide in a NuGet package a partial class, then other people can extend it. But I also find it useful for kind of splitting up what's going to be a very large file. So it doesn't reduce the size of the class overall, but it does make things more manageable. So I can start to bring out, if I want to find the instructions, I don't have to scroll through 500 lines of code. It's in its own file, but it all comes together when it gets compiled. So it's very good. We've also got a test project, which is Z80.tests, and the idea of this is that we're going to try and build this in very much a test-driven manner. So we've got some tests already created, and we're using what's called Fake It Easy, which is our faking framework, which I tend to favour. Okay, but I'll explain a bit more about what all these things actually do in a moment. But first, I want to just concentrate on this interface iBus. So the reason why we've got an iBus interface. So if you can think of a CPU. Let's see if we can draw a CPU. Here's a CPU. It's a wobbly CPU. Z80. Okay, that's our CPU. Now that has to speak or communicate with other devices, such as the video memory, printers, other peripherals. There's no mouse or anything like that, but there's a keyboard obviously providing input. And so how it does that, it connects to a data bus, which we can kind of conceptualize as just being a connection. So in fact it's slightly more complicated in reality. There's an address bus and a data bus in the actual architecture, but we're not going to worry about, we're not trying to recreate the hardware. We're just trying to emulate the hardware in software. So we can think about this as being a simple connection like that. So that's our bus, and we have devices attached to that. 5 Creations, welcome to the stream. I've not seen you before. Flav Creations, sorry. You may have been in the stream before. So do forgive me if you have. So welcome to the stream. Good to see you. If you're not a follower, then please do click that follow button. We're rapidly heading towards our months ago was it Flav Creations? Yeah. So we're rapidly heading towards our kind of 300 follower target. So it'd be great if you would follow if you don't already follow. So yeah, we're just starting on Oh yes, Gareth Stream. Yeah, I do like Gareth Streams. They're a great deal of fun. And you're already a follower. That's brilliant. So what was I saying? Yes. So at the moment, though we could have other things attached to this, we could have printers, whatever. We're just going to consider it that it's got a big blob of RAM attached, like that. In fact, we're not even going to model that. At the moment, all we've got is this iBus interface. So let's just have a look at that. So all the iBus interface does really is define two methods, read and write. We're going to be able to write data onto the bus. It's going to go somewhere, and we're going to read data from the bus that's coming from somewhere. We don't know where it's coming from yet. So this is going to have to kind of grow in complexity a little bit. Your devices attached to the bus are going to have port numbers, and so you're going to be able to write to a port. So you might have, we've all heard of printer ports. There's actually it's a physical address in your computer where data gets written and it goes onto the printer or gets printed. The printer kind of has its own memory. It takes care of all the details of actually producing the print, but you write your data to that printer port and it will get printed. Along with all the control signals to the printer to start, to stop, all that kind of thing. And the printer also communicates back to the CPU, maybe with what's called interrupts, to stop the CPU doing what it's doing and to kind of service the printer or the other device. Now, interrupts are a whole kind of new kind of area to look at. We're not going to do interrupts immediately. We're going to kind of leave that for much later in the stream, or in the series of streams. That is when I build this emulation. But that's basically all we've got in terms of our bus. It's somewhere to read data and to write data. So over in our main class, which is the Z80 class, we can start to think about what actually a CPU is, what's inside a CPU. And obviously, this is by modern standards, a very simple CPU. It's an 8-bit CPU, so it's old technology, but it was actually quite influential at its time. How many streams do you think this would take? Yeah, it's a bit how long is a piece of string. It's not it's not something I can build totally on stream, because I think people would find it very boring to keep just working through the hundreds of instructions and adding them one by one, tests, and then adding the instructions. So it'll be something we'll dip back into, but I think it's going to take quite a long time, and it's going to get kind of more complicated when we start getting to the more difficult instructions. And it may be that we have to kind of start to reach out to the emulation community for some answers to some of the questions that are going to crop up. One of the interesting things about the Z80 is that it's got undocumented features. Things happen inside there which weren't part of the original documentation. Luckily, there's lots of people have been doing kind of work on this subject over the years, and they've actually documented the undocumented features, so we'll be able to reach into that. There's also bugs in the hardware, so and in the kind of the programming of the chip itself, and we want to emulate the bugs as well. We want it, if it originally crashed on the Z80, we want it to crash on our emulation, because we're trying to do a faithful emulation. Now, how that'll work out, who knows at this stage. We're in that kind of first flush of optimism of the project. We haven't come across the really difficult parts of the emulation. We're just starting out. I believe there are some C# Z80 emulations out there, Rambling Geek, but I want to do put my own spin on how to emulate something and how to construct the classes. And also, I want it to be a NuGet package so that people can include it in their own projects and don't have to kind of don't have to compile something separate to do the emulation. It may well be that the C# emulators that do exist are available as NuGet packages. I'm not quite sure, but yeah, it's just because somebody's already done it doesn't mean we shouldn't do it as well. And we'll put a different spin on things. Okay. So I'm using Coderush here, so we can embed images inside our code. So we'll start off. The actual architecture of a CPU is relatively straightforward. Basically, it contains some read-write memory of its own. So a Z80 needn't have any RAM associated with it. It can just be a read-only memory-based system. So it could have a Z80 processor and a ROM or an EEPROM or something on the board, and it can run the programs which are in the EEPROM. Of course, it does need some read-write memory in order to do calculations and things like that. So what internally the chip has is a set of what's called registers. Now inside the Z80 we have this. So I think I can make this a bit larger, shall we? Let's see if we can just make this a bit bigger so you can see it. Okay, we have these registers. We have a main set and a shadow set. So we have an accumulator, and the accumulator is basically where where calculations are accumulated. So if you're kind of adding two numbers together, you have the first number goes in the accumulator, and then you run an add command and a number, and give it a number, and that number gets added to the accumulator. So if you had 2 in the accumulator and you added another 2 to it, the accumulator would suddenly have 4. So the name accumulator is quite appropriate. But there are also other registers. So these group here, along with their shadows, are what we call general purpose registers. So these are used mainly to hold intermediate values or to shunt data around. So you've got your accumulator, which is where we add things up or subtract things. So we do kind of calculations using the accumulator. And then we've got these general purpose registers as well. And these are all 8-bit registers. So B and C, D and E, H and L, A and F are all 8 bits. And so are their kind of what the primed values here. These are the shadows. Now the shadow registers we don't, as programmers, have access to directly, although in my emulation we will have access to them. The main reason for that is we're going to want to build some kind of GUI where we can actually see the internal workings of the memory and the registers of the CPU, so we can see it stepping through programs, see the various registers updating, the flags changing, and all that. So we're gonna need that kind of feature to be able to get at these registers. And also in our test harnesses we're going to want to be able to set them, so we need to kind of set up a scenario to start a test. So we do have access to all of these registers. So the interesting thing about these B, C, D, E and HL is that we can also access them as a pair. So that's a 16-bit register at that point, and this is quite interesting kind of development for the from chips like the 6502, which were purely 8-bit. Now we've got some kind of 16-bit capability. The F register is interesting. That's what's called flags. So that's basically an array of bits, 8 bits, and it's used to record various conditions that happen inside the CPU as it does various calculations. And I actually listed all those flags at the top here. So the first bit is what we call the carry flag, and this carry flag gets set if when we do an addition, we generate a carry. So we need to carry 1 across. So maybe it's binary addition we're doing, and the same with a subtraction. If it generates a borrow, then we're going to set our carry flag. So when we start to emulate all the instructions, we're going to need to know what those instructions do to our status registers here. But we have a carry flag there. Then we have what's called the N flag, which is an add subtract flag, and this is used by one of the commands, which is to do with binary coded decimal. So this is a complexity which we're going to have to kind of deal with eventually, but we're not going to kind of do initially. We're going to stick to the simple commands, and then start, as we kind of get experience with working with the emulator, we're going to kind of build that up. Next we have a parity and overflow flag. So if we add two numbers two 8-bit numbers together, and they overflow. So we add 3 to 255. We're going to overflow the capacity of a byte to hold the result, in which case we'll set the overflow flag so that we know that we overflowed. Also, when we do logical comparisons, we also use this same flag for what's called the parity. So if when we do the logical comparison of two binary numbers, then if the number of bits that are set to 1 as a result of that is even, then we can set the parity flag, and if it's odd, we unset it, set it to 0. Then we get an undocumented flag. It seems it holds a copy of bit 3 of any result, which is a bit odd. And there's a further undocumented one here which holds a copy of bit 5. So although the official documentation, such as this book, well, it's not particularly official, but this book says we don't use these bits, they actually do get set to values, and we're going to emulate that as well, so that anything that which kind of clever programmers might have done to kind of realize that's happening and to exploit it, is still going to work, and anything which internally actually depends upon that flag being set, even though it's not documented, then it'll still work. We have got something called a half carry flag, which is to do with binary coded decimal as well, so we're going to kind of park that one. If the result of any calculation is 0, then we set the 0 flag, and the sign flag, this stores the most significant bit of any value that's in the accumulator, which is register A. So this is basically saying that if it's a signed value, then a 1 in the most significant bit, it indicates that it's a negative number. Okay, so if we're doing subtraction, for example, we say 1 add -5 is going to be -4, so we'll have a 4, and the signed bit here will be set. Okay, so that's our main set of registers and the shadow equivalents, and I'll show the definitions of those shortly. We also have a number of other registers. So there's the index register X, index register Y. We have an interrupt vector, which we're going to park. We're going to read up about that, see what that is. A memory refresh register, which likewise we're not going to go into in the initial streams. But the important ones for this special purpose group really are the stack pointer and the program counter. So the program counter simply points a location in memory where the first instruction of your program sits, and then it increments through your entire program. It goes up and up through the program, and then it might hit a jump and be redirected somewhere else while it services that jump, or maybe it's a subroutine and it goes off somewhere else, does the subroutine, and jumps back where it came from. The stack pointer is kind of the key to those kind of jumps, especially where it's got to return back. We can push values onto the stack and then pop them off again, and it's a last on first out kind of LIFO stack. So you push things into it in layer, like a layer. So you push things onto it and then you pop them off in the reverse order that you push them on. So those are the main registers that we're going to emulate. The important things for the current commands that we're working on are these set of registers here: the accumulator, the flags, B, C, D, E, H, and L, and the program counter. Currently, we're not using any of the shadow registers or the index registers or such things. The stack pointer, we're not using the stack at the moment. But today, I'd like to kind of venture into unknown territory and do something with the index register IX, because we're working on load commands today. So let's have a look at what else we got. So here's our general purpose registers. So we've got the accumulator, which we initialized to have 0 in it. We've got flag register F, and that's of type flags. So that's of this array of bits. So we need to be able to kind of detect whether one of these bits is set or not, and set and unset those. So we need a function to do that, make that easy for us. Then we have all the rest of them. We have the shadow versions of the same ones. Then we have our special purpose registers. So we have the interrupt vector and the refresh register. Then we get a set of 16-bit registers: index Y, index X, the stack pointer, and the program counter. And these are 16-bit because they hold a memory address, basically. That's how they work. And I did mention that we can actually then also view BC, DE, and HL as 16-bit registers. So in order to make that really easy, then we've just made this combination. So HL is the combination of H and L, BC is a combination of B and C, and DE is a combination of DE. And then we've got the shadow versions of the combined registers. And what the shadow versions are all there for is basically what we can do. We can swap the, say, HL into HL1, and that's why we've kind of preserved the state of HL. So we might swap all our registers into their shadow versions, do something, service an interrupt, do some routine, whatever, and when we've finished that, we can come back and swap them back into their kind of saved state and carry on. So it's quite an interesting kind of architecture that you can do that. And I think it was one of the, I don't know if it's the first to do that kind of idea, but I know that, for example, the 6502, which is the one I've got more kind of experience programming, has got nothing like that. So you have to save things to memory. And obviously saving things to memory is more expensive in terms of CPU clock cycles than actually keeping things within the chip. So you're not having to go onto the bus, write things to memory, and then read them back again once you've finished your subroutine or your interrupt. So that's, I think we're going to have some music. I think let's get some music going. Bit of relaxed daily, that's nice. Okay. So, what else have we got? So we've defined a private variable for the bus, which is of type iBus, which enables us to kind of expand on our definition of what a bus is later. But there is no concrete implementation. It's just an interface at the moment. So do note there is no concrete implementation of iBus. So there's no bus.cs class yet. It's because at this stage we don't need one. We don't need to know how that works yet. We just need to know it has a read and write method on it. Then we've got some other private variables. So we've got an absolute address private variable and a relative address. So currently we're not dealing with relative addresses, but absolute address, which we initialize to zeros. It's of type ushort, unsigned short integer, so it's 16-bit unsigned integer. The current opcode we're processing is stored as a byte here, and clock cycles is how many clock cycles each command is going to take. So you probably know that a CPU is contains an internal clock. This is where you say I've got a 4 gig processor. It's 4 gigahertz processor, so that's how fast the clock is oscillating. Each of those clock cycles is used to synchronize your commands with any peripheral devices which are also kind of working with your CPU. So your memory, any kind of I/O chips, anything really connected to your bus. So they can work together. So it's a timing feature. So we need to know how many clock cycles each part of a command takes. And basically, this is to make sure that we don't run into any issues in the emulation where two devices are trying to do the same thing at the same time. So I'll show you how that works in a second. And then in the constructor, we start to build up in this case we're using a dictionary which shows all the commands available to us. So these are the commands I've programmed so far. You might think there's quite a few, but actually that's just scratching the surface. So it's a dictionary of byte and instruction. So byte is the key, and that is the operation code. So this is what is actually in memory. So for example, if the program counter fetches a command and the opcode for that command is 0, then that's no operation. Okay. Likewise, if it fetched 3E as the opcode for memory, which the program counter has pointed that memory location, it reads that in, then that's a load the value n into the accumulator. Okay, A. So this mnemonic is the assembly language, and the whole reason for having this dictionary is not just to make it easy for me to kind of find out what to do when I read an opcode, but it's also so we can have a disassembler. So when we've got a bunch of opcodes, we can use this dictionary to actually print out the mnemonic here, so we can actually make the opcodes readable when we try to debug something. So let's have a look at the instruction class. This is basically it could be a struct rather than a class. So what we're saying here is that an instruction is made up of 5 parts. The first is our mnemonic, which is a string. So this is just to make it readable to us as humans. We have an addressing mode. So how are we going to get any data that's associated with this command? So there are a number of different addressing modes, and with the Z80, any command can have more than one addressing mode. So it might get one part of an operand from using one addressing mode, and another part or another piece of information using a completely different addressing mode. So we have 2 addressing modes associated with an instruction, and these are represented as funcs that return a byte. Okay, so then we also have the operation itself. This is represented by a func that returns a byte and takes a byte, and the reason why it takes a byte as an argument I'll come back to shortly. And then we have how many what's called T cycles or timing cycles that an instruction is going to actually consume. So for example, no operation consumes 4 clock cycles, and 4 clock cycles at 4 megahertz, which is what the original clock speed of the process. That's about 1 microsecond, isn't it? Something like that. Okay, and then we've got a constructor for that. So you may wonder what on earth is an address mode, and why is an operation taking something that returns a byte? That sounds reasonable, but why does it actually take a byte as an argument as well? Let's look at address modes first. Okay, so there are a number of address modes, of which I've only coded a few, as you can see. So the first address mode that we've got is called implied or implicit address mode, and this means that basically the command itself implies an address, or implies where data is going to be processed from. Just it's part of the command. There's a very similar addressing mode called register addressing, and you can see that actually the implementations of these two, implicit addressing and register addressing, is identical. It simply returns the value 0. It doesn't actually do anything. What I can show you is examples of both implicit and register addressing. We'll do that shortly. There's also immediate addressing. So immediate addressing mode means that the byte following the opcode is the data. So it's quite obvious. So if we got opcode 59, and that's an immediate addressing opcode, then the very next byte is the data we're going to work on. And we've got some examples of that. There's also immediate extended, and what this means is that the next 2 bytes after the opcode contain the address where the data is going to be found. So for example, if we had, I don't know, opcode 64, and then we had 0010, then that means we form an address out of that. So that would be in hex 1000. We go there and find the operand we're going to work with, the data that we're going to work with. So that's what this piece of code does. It basically, we take the low byte, increment the program counter, get the high byte, increment the program counter, and then we form an address. And we store that in that private variable absolute address. Okay, so this is some memory manipulation we're doing here, some bit shifting to form an unsigned 16-bit integer, which is going to be placed in memory. We're going to go to find our data. The only other addressing mode I've got built so far is register indirect addressing, and this current version, this version here, is based upon the HL register, which you remember is the combination of the H and the L registers viewed as a 16-bit address. So basically, whatever's in HL is our absolute address, and we populate absolute address with that, and we return 0. So returning the value currently has no effect, but I've got kind of thoughts about why we should return values from our functions. So don't concern yourselves that it's returning a byte, but it's always returning 0. There's that may go away in the fullness of time, but I've got some thoughts about why that might be useful. So those are our addressing modes, and if we go back to our Z80 class, in fact I'm going to just undo the change to this, which I think was just resizing that picture. Let's come back. So you can see, for example, here for the no operation, it's implicit addressing for addressing mode 1 and 2, and we've got an opcode of NOP. So remember, these are funcs, yeah, and it's going to consume 4 clock cycles, 4 T cycles to do that. So this defines the addressing modes we're going to use and how many clock cycles, and then we can kind of consume this this dictionary and run each of these functions as we need to. So over in the instructions, if we look at, for example, no op is very, very simple. It doesn't do anything. By definition, no operation does nothing at all. Okay, it doesn't affect the flags. The addressing mode is implicit, so there is no data to process. So we just kind of do nothing and then go on to the next command. Halt is an interesting one, which I've coded as it's basically the same as NOP, except that this is a great way of getting into an infinite loop. So this will put the processor into a state where it just does no operations. It doesn't increment the program counter. It just continues to do no operations. You may think, what on earth is that about? Well, it's all to do with interrupts. And I say we're parking interrupts till I understand exactly how they're going to work in an emulation. Because we're not really dealing with real peripherals that are going to interrupt the processor. So it may be they're not needed, but we've got everything kind of set up so we can emulate every command. So the kind of group of commands I'm working on currently, I've just started, is what's called the 8-bit load group. So these are a set of instructions which are going to manipulate, which are going to load 8-bit numbers, one single bytes, into registers or into memory locations or whatever. So there's a whole kind of batch of these. If I go over to this document here, we can see this is the Z80 CPU user manual. It's available online. Just do a search for Z80 user manual and you can get a copy. It's very similar to this book. Obviously this book is not easy for me to share on screen, but this is a lot easier to do that. And you can see that there are a bunch of commands in this 8-bit load group. So these instructions are described in the pages that follow. So there's, for example, the one that I've done here. This is load the contents of a register R with the contents of a different register. So basically, wherever R prime is gets loaded into R. The opcode is LD. The operands are R and R prime, and it's a single byte command. So there's no finding where the data is. This is what's called register addressing mode. So within the command itself, the first three bits of the opcode here define the source register, and the next three define the destination register. And to find out what register that means, you just use this little table. So if this contains 7, for example, 111, then that means register A, the accumulator, is our source, and the destination, for example, if it was 010 in here, that would mean D. So copy the value that's held in register A to register D. And you can see that this little table of values here means that you get quite a number of different opcodes that are generated just from this one command. And you also get nonsensical opcodes. For example, if it was all 1, so 01, 111, 111, that would be copy the value that's in the accumulator into the accumulator, which is effectively a no operation. But it is a genuine command. It is available for you to do that. So the example they give here is if H contains 8A and E contains 10, 100, then the instruction would of load H, E results in both registers containing 10 hex. Okay, so the contents of E were then moved over and copied into register H. So we haven't destroyed the value that's in E, we just copied the value over into H. So what does that look like in code? We can also see here that it takes one machine cycle, which is 4 timing cycles. Okay. So what does it look like in code? Well, it's really very, very simple. All we do, and I've definitely represented this by a function called LDRR. If we were looking at F#, we could actually have the prime against that, but we can't. So it's just LDRR. So load register from register. So basically, we use this mask here to find out what the source is. We use this mask to find out what the destination is, shifting across to the right by Anti-Sebo. Thank you very much for that follow. Have some electric L5, so thank you so much. Very kind of you to follow. Yeah, so we're going to take the value of this mask here, and we're going to shift it right by 3, so we get a number which is between 0 and 7 inclusive, and then we can use these functions here to go and read and write the register. And all that these do is it's just a switch statement. So read from register. You'll notice the 6 isn't a value here, but basically go and get the value that's in B, C, D, E, H, L or A, and then write it. Write a value, a byte, to those register locations. And these, as you can see, are single byte assigned. So we will eventually have assignments to the grouped register, the 16-bit registers. We'll group B, C, D, E, and H, L. We'll have to have some additional overloads of these functions to do that. Okay, so the next command is load a register with a value n. So if we go back over here, the next page, LDR, n. So take a value n and load it into a register. Once again, the register we're going to load in, the destination, is these kind of middle 3 bits of the opcode byte. The end of the first 3 bits, right, rather, is the 6, which was missing from our table. That's basically saying that the value you're going to load is going to be in the next byte following the opcode. And you can see that's represented here by n. This takes 2 cycles, 7 timing cycles, 2 machine cycles. So 4 to read and carry out that instruction, and then a further 3 clock cycles, timing cycles, to actually grab the data out of the next byte and pop it into the register. So quite strange. You can also see we're noting here that condition bits aren't affected. So these flags that we set up at the beginning, the carry flag, the 0 flag, whatever, they're not affected by these loads. Which is useful to know, because you might think if you load 0 into the accumulator example, you want to set that 0 flag, but this is saying no, we don't set any flags with these operations. So this is what we call immediate addressing mode. So immediately following the byte basically is going to be something to do with where you get the data from. In this case it is literally the next byte is the 8 bits of data. So if we go over here, we can see that in the over in the instructions, here's for example is the command load the accumulator with the value n. This is opcode 3e. It's immediate mode. We've got a second addressing mode even though it's not used, and the function we're going to use is load rn, and it takes 7 cycles. Okay, so that's that. So if you're wondering where these codes come from, it's simply by calculating, looking at that these various values and working it out. That's pretty tedious to do. So we've also got a bit of a cheat sheet here. So we've got a list of all the opcodes. So we can see here, if I go down to 3e, it's load the accumulator, and this is a rather odd notation, ampersand 00, but it just simply means it's going to be the byte immediately following the opcode. Now from this table you can see there's a bit of a wrinkle with the Z80 instruction set. You can see here we go down all these various codes, we eventually get to FF, and that you think that's the end of that's the last there's only 256 instructions we can have, but that's not the case. We also have extended functions. So there are 4 bytes which don't actually represent an opcode in their own right. So there's CB, DD, ED, and FD. And these basically extend the number of commands available to the Z80 programmer by a huge amount. So these indicate, if you see CB for example, then that means we're going to, the next byte contains a completely different table of instructions. These are the CB instructions. Okay, if we scroll to the top, here's the CB instruction. You can see that there are basically another 256 instructions there. Go all the way down. So now we've got 2 lots of 256 instructions, but it gets even more interesting because if you prefix with FD for example, you get another 256. If you prefix with ED you get a smaller group, mostly, and with DD you get some additional commands here. So there are quite a number. You know, there's in excess of 500, 600, 700 commands that we've got to code. We've got to code each of these. Now luckily some of them can be kind of done in one simple function, but others are going to need more thought. So it's quite a lot of work to do, which is why when Rambling Geek asks, how long is it going to take, how many streams will it be until you've got an emulator, I've no idea. I don't know how long it's going to take. It's going to be pretty boring for people to watch me do all of them, so I should be dipping in when I start to get to what I consider to be interesting commands. Then we'll kind of dip back into the project onto the stream and actually do that. And when we start getting some output and start building some, I was thinking of building a WCF desktop app to actually run the emulation and to be able to interact, step through programs, and also to do this disassembly so we can see the program disassembled on the screen. So I've got quite a lot of plans. It's going to take quite a long time for those to come to fruition, I think. Okay, so we've got a list of opcodes, which is kind of a bit of a cheat sheet to help us out. So where did we get to? Okay, so you can see these are the commands we've done so far. So there's a reasonable number of commands covered off. The next command is load a register from whatever HL points to. So HL is one of our 16-bit combination special registers. In brackets, it means that the contents of HL point to a memory location, and that's where you get your data from. So that's what. So interpret HL as a memory address, go and fetch the data at that location, and then load it into a register, register R. And that uses basically exactly the same things. We form a fetch command. The fetch command basically is sensitive to which addressing mode we're in. It will go and get the data, return it as N there. That's a single byte that's returned, and then we basically assign that byte to the register. So that's quite straightforward. And if you want to go over here, we can see the fetch command in action. So simply all we're doing is saying unless we're doing implicit mode or register mode, then we're going to actually execute addressing mode number 1, which is why this is fetch 1, and then we're going to read from the bus whatever's at that address and return it. Otherwise we simply return a default value of 0, because we're not actually interested in returning a value from the fetch. A couple of the commands we've got, methods we've got here, we've got connect to bus, which basically will connect us to a bus. In this case it doesn't exist, it's purely for testing purposes at the moment. There will be eventually a concrete class for bus, which enables us to connect kind of devices, software devices to that bus and then interact with them. We have a tick command, which basically is each tick of the CPU's clock. We call this, so this will be a kind of big loop. Initially we'll step through, so we'll tap the space bar and step through ticks of the CPU. And basically what happens here is we read the current opcode. We need to do something here about interrupts, but we are not covering that at the moment. We also need to do something about multi-byte extended opcodes. But if it's a simple what's called a root instruction, then we're able to simply process it. So we get how many clock cycles it can take, we perform the instruction, and then we decrement our clock cycles, and then once we go through this loop, each tick, and then once we get to 0, we can accept the next command. This is our kind of a timing control loop, really. We have commands here to read and write from the bus. Currently we're not using the write command, we're just reading, and this simply just calls the read command that's on the bus. So the I bus has a read and a write method on it, so we're simply just doing that, doing those. And then we get check flag, so we can pass a flag in and say, is it true or false? I've got this is alternate. Are we using the alternate or the shadow registers? It's probably not going to be necessary because we shouldn't really interact with them. They're really for copying the state across, but I've given myself the ability to do that. It may go away. And we can also set the individual flags. So a bit of kind of bitwise operations going on here with the bitwise and here we've got a bitwise OR and a bitwise and with the negation here. Okay, so that's fairly straightforward. So let's kind of dive in and actually build a command. So we can kind of have a look at a slightly more complicated command, I think. So let's go over to our user manual, and the next command that we need to look at is this one. This is load a register with the contents of the memory address pointed to by the index register IX, but add to IX a displacement D. So D it can be a positive or negative number. So we're going to first have to look at whatever's in register IX, form a memory address from that. We're going to add a displacement plus a positive or negative displacement to that address, which will shift the address up and down, and then we're going to go to that memory location, read the data from it and put it into register, whichever register R is. Once again, you can see that register R is these middle bits of the opcode. Immediately following the opcode is a value for the displacement, but this command actually consists of 2 bytes. The very first byte is DD. So this is one of these extended commands. This is one of the ones where we need to kind of have a separate table of opcodes. We need to detect that we've got a DD in the first byte, and then look up increment the program counter, read the next byte, and that's the command on a different lookup table. So the idea here is that we're going to take the contents of the IX register, and we're going to add what's called the 2's complement displacement register, displacement into D, to that to get an offset. So 2's complement is a way of representing negative numbers in binary. So if anyone doesn't know what 2's complement format is, just let me know in chat and I'll try and explain it. We've got the similar table as before to determine which register gets loaded. And you can see this takes 19 clock cycles, 19 T cycles. It doesn't affect any condition bits. And the example they give us is if the register IX contains 25AF in hex, the instruction LDB IX plus 19 hex, 19 hex, allows the calculation of the sum. So we add 25AF and 19. That points to memory location 25C8, and we read the value that's in there, and that contains 39. So we load register B with 39. So it's indirect kind of way of getting at our data. And you might be thinking, what on earth is that all about? Well, if you think if you have a kind of a list or a table of data, this displacement, this D, enables you to start at a base location, which you load the start of your list into IX here, and then you vary D, and you can scan backwards and forwards through that list. Okay, so that's the idea of it as a command. We're at a very low level, remember here. This is assembly language, so every little thing you need to do, you need to kind of code. So this is like an iterator or a numerator or whatever. Okay, so how are we going to do this then? Okay, let's have a look. So let's go here. We'll go over to our addressing modes first. So this is an indexed mode, isn't it? So the first thing we need to do is actually recognise this DD byte. So over here, the first byte, the opcode read is going to be DD. So let's have a look at just recognising that first. So over on the Z80 class here, here we've read the opcode. We're handling the fact if that's a halt command, a halt opcode. But here we say we need to handle the multi-byte extended code. So we need to do that. So DD is one of them. So let's just figure that one out. So we're going to do the simplest thing that could possibly work, which is my kind of philosophy when coding. So if current opcode if that equals DD, then we know we've got one of these extended ones. Okay, so what we're going to do is we're going to put an else, and we're going to tidy all this up at some point in the future, but we don't want to be needlessly refactoring until we've got tests which support our refactoring. So that's one of the important things, that we're going to build all the tests first before we actually implement the actual commands. But we need to do some plumbing work first to make sure we can actually detect it. We also need another dictionary. So let's have another one of these, and this is going to be Didi Instructions. So we're going to have to read our instruction kind of class here from a different lookup table this time. Okay, so if we've read a DD, what we need to do is then we need to kind of read another instruction. So now we're going to update current opcode by reading from the bus. So we're going to need to increment the program counter, aren't we? PC++. We've incremented the program counter. Read the next byte, and the next byte is going to be our actual command, and we're going to look that up on our new DD table. So it's going to be DD, and we're going to get the number of clock cycles that the command takes, number T cycles, and we're actually going to execute the operation. Now you notice here, this is the operation, this is the function that we're calling, but we're passing the opcode into it. And the reason we pass the opcode into it, because the opcode actually contains data as well. It tells us which register we're going to be updating. So this is why back when we defined an instruction, which is over here, this is why it's defined as a func which returns a byte but also takes a byte, because it consumes its own opcode, because that gives us valuable information. Okay, so that basically is what we need to do in order to execute the extended codes with the DD prefix. So that's quite simple. Let's go over to our instructions here now. So this command, it was LDR IXD, wasn't it? So let's create a new we can copy this one. I think it's going to be very similar to this. So this is an instruction is load a register with the contents of the OS pointed to by IX with a displacement. So what we'll do is we'll remove that comment and we'll figure out a better comment eventually. So there's no flags that are updated by this command, so condition bits were unaffected. So luckily, so far we haven't had to worry about that. Cody Bird, good to see you. Nice to see you enjoy the stream. So this is we're working on what's called Project Z. This is our Z80 CPU emulation. It's a project that's just started. So thanks for joining. So we need to think of a function name for that. So we'll have LDR IXD. I think is probably okay. We get the opcode. Once again, we get our destination. So we've already got this piece of code here. And now we want to go and get the value of n. Okay. So n is going to turn out to actually be d, isn't it? It's going to be our displacement. So let's go and have a look at what we do in terms of what we're going to do here is we're going to comment out all of that, because that's an implementation. We don't want to do an implementation yet. We want to go over to our class here, and we need to figure out what we put in our into our DD instructions. So underscore DD instructions. That's going to be a new dictionary. Byte instruction. Okay, and we're going to have a number of these. Let's just find one of them. So we'll find that one that loads the accumulator. So it's one of these ones over here. IX plus A. That's it there. So this is the command we're going to start off with. That's 7777 in hex. That's DD77 is the full kind of 2-byte operation code. So 77. Oh no, that's the other way around. It's this one here. It's 7E. Load 7E. So remember, it's the destination followed by the source. Okay. 7E. Okay. So let's add that to our list. So first is a mnemonic. So we have 0x7e. 7e. And then a new instruction. The mnemonic, which is ld a comma ix plus d. We've got some kind of mode for addressing. So let's go back and have a look. Addressing modes. So if we back here, addressing modes. Yeah, okay, so which one of these is it? So it's not indexed. So we're simply going to read the next byte actually to get the displacement, so it's not as hard as it sounds. Okay, so this is immediate mode. So we're going to put that in twice because some commands can have multiple addressing modes, and then we call this ld rxd. rxd, and it was quite an enormous number of cycles. I can't quite remember how many it was. I think it was 19 cycles. Yeah, 19 cycles. So Coderush, you saw the last shader stream. Yeah, it was amazing, wasn't it? I was just really impressed. So we're gonna work on that a bit more. So we got the snow on the mountains looking really nice on that shader. What we want is to put some clouds in the sky. We want some vegetation. We want some waves on the water, some sparkling on the water as well. So I'm hoping that particular shader, when we're done with it, is going to look really, really nice. And it's a great starting point for people who want to go and play with it, because it's not up on Shader Tour yet. It will be when it's finished. The current code as a CodeLife project file is on GitHub. I think it's called Codebase Alpha 6. But yeah, if you haven't checked out that stream, the last stream, it's up on YouTube. Episode 65. Part 4 of our series on pixel shaders and ray marching. We did a mountain range. We started off, I think, with sand dunes, and then we changed it into a snow-capped mountain range, and we had some sea and all that kind of stuff going on. So yeah, it's absolutely wonderful stuff. I was kind of really buzzed by that stream, and in fact found it difficult to get to sleep that night because I was so excited about what we managed to do in just, I think it wasn't even the 3 hours. I think we started off doing some other stuff. In the event, I think it's about 2 hours work to get to that. It was quite amazing. Yeah, so 19 is the number of T cycles this is going to take. And okay, finish there. So that's our instruction. So there's going to be a whole set of these. Interestingly, that this command is also 7E, so I'm wondering if there's a pattern going to form. So let's see if there is a pattern. Go over to our opcodes list, and if I look at the next one here that's similar, so load register L with the contents of pointed to by HL is 6E, and 6E is exactly the same thing, except it's the contents of our index register and the displacement. So I think we can actually infer that. so we should be able to fill in all the rest of the commands actually. So let's do that. So we've got B, C, D, E, H and L. So that's going to be 6E. 6. Let's just check that just to make sure we have got the right pattern. 6, 6, yep, that's H. This was L, load to register L, load to register H. So there definitely is a pattern, so it's nice when there's patterns like that. So 6, 6 was H, E was 5E. This way we get kind of 7 commands for the price of 1, which is really quite nice. But there we've got C is 4, D is 5, 6, and there'll be 4E and 4, 6. I should imagine. So that'll be B. C, D. C sharp Fritz raiding with a part of 80. Welcome indeed. Welcome indeed. So that's amazing. Thank you so much, Jeff. That's fantastic. And thank you for the follow. That's some Electric Alf to welcome to the stream. The coding squad's here. Yeah. So you find us in the middle of working on our Z80 chip emulator. Thank you for those cheers, Kerry. That's very nice of you. So hopefully the bot is responding to your messages and posting a little welcome message. Foachon, thank you very much for the follow. Have some more hype, Electric Alf hype. Yeah, we're building a Z80 emulator. We've only just started, so it's not very far along. Oh, who was that? Shah, thank you very much for the follow. Excellent. In fact, let's have some hyperspatial hype for the raid. This is one of our shaders that has been built. So we are working on shaders part-time on the stream as well. So .NET Dev, thank you very much for the follow. We're racking up the follows. That's fantastic because we're aiming for that 300 and we're now at 92% of the way to that 300. So thank you so much for the follow. It's really appreciated. Alka, thank you for the follow. Let's have some Electric Alf. So these effects you're seeing on the screen, it's probably degrading the stream slightly, but these are real-time WebGL shaders, so they're not GIFs or movies. They're actually in real time. FR3, thank you very much for the follow. That's fantastic. We've got a follow train going on, so thank you so much. Valerian, thank you very much. Let's have some more hype. Alka, you only dipped into showing the shaders. Yeah, so if you check out our YouTube channel, which I'll pop over here, you can see that we've done 4 episodes so far. So the very first one was a 2D kind of kaleidoscope that we did. Then we did a cube and some spheres rotating around the cube and morphing inside the cube. Third episode we did similar thing, but we actually made the sphere and the cube. We kind of sculpted the cube, made the cube and the sphere reflective, put some light sources, 2 suns, the light sources, and then we actually took the materials involved into account when we did the reflections. So that's all there. And then last stream we did mountain ranges. In fact I can show you some of them because they're on Shader Toy. Let's just take a quick diversion from what we're doing. I'll take you to Shader Toy. In fact, we'll use Chromium Edge for Shader Toy. Just to give an idea of what's up there, and all the code is available on GitHub. So do check out the code as well. So let's go and have a look at my code that's on. And some of these are fantastic. I mean, look at that. This is all real-time stuff. This is not, there's no models involved. This is all mathematically generated. So this was the last one, the one we did before the mountain range. This is a reflective sphere rotating around this sculpted box, which is also reflective. There's two suns in the sky, and we have a plane surface here, which is less reflective than the objects that sitting on top of it. And you can see it's reflected in all locations. You can sit and watch this for hours actually, looking at all the reflections. And this is the code over here, and you can see this is 207 lines of code, and there are some commented out areas as well. And that is running. That's a single-threaded program that's running on every core of your GPU. So there's teraflops of processing going on just to display this, and this is the power of those GPUs you've got in your computer. And in fact, this actually works okay on a mobile phone as well. Insomniac, thank you very much for the follow. That's wonderful. Yeah, so I can show you them. I don't know what it'll look like. Let me show you the mountain range as well, so that you get an idea what that looks like. The Chronicle, thank you very much. This is the mountain range that we built. So we're using CodeLife, which is a fantastic IDE for building shaders in, and this is what we built on the last stream. The code for this will be up on Shader Toy probably after the next one, because you can see it's a work in progress in terms of the water doesn't sparkle, there's no waves on it, there's no clouds in the sky, but we have some beautiful effects on the snow. There's both specular and reflective lighting going on, so it's shining off the snow beautifully, and it's nice and smooth snow. You'll also notice that we take into account how flat the terrain is, so the snow sticks to the flat terrain and doesn't stick so much to more vertical terrain. So yeah, so Valerian, the shadows are amazing. Yeah, they are, aren't they? Use the classic pipeline actually. Forget what we can do with shaders. So this is all mathematics. Yeah, it's all mathematically generated in real time, 60 frames a second. So this one here is 310 lines of code. There is some repeated code in here that could do with a bit of a refactor. We've got different height functions, high fidelity, normal fidelity and low fidelity height functions going on. It's all based off a Perlin noise texture. So the height of the mountings is based off a texture. Lazarus, thank you very much for the follow. Let's have some more. Electric Elf, which is also a shader. So two shaders running at the same time, probably really ruining the stream at the moment, but I think it's worth doing. Calameo, thank you very much for the follow. It's wonderful. Well, we've wrapped up. We've really got, what, we're 95% of the way to our target. That's absolutely amazing. So thank you so much, guys. So thank you, Jeff, for the raid. It's wonderful. Okay, I'll try and get back to the thread I'm following. So back to our Z80 emulation. Alga. So you appreciate it's fully written out. Float values. Zeros on both sides. So yes. The reason why I'm trying to do it that way is because it makes it easier to translate to Shader Toy, which only accepts float values. So I do try to remember when we're building on stream that we have the 0.0 whatever. It doesn't always kind of work that way. Sometimes we forget. We have some integers in there, but yeah. Okay. Right. So we've got the kind of the basic instruction codes here. These are the opcodes, and we've got our instruction, which is currently doesn't do anything. It doesn't simply return 0. So we should now be able to go to our tests. So this is our test suite for the 8-bit load group. We name it 8-bit load group should, and then for example here, load A from B when operation is load A from B. So we need a new command, a new test. So what I'm going to do is copy this previous test that we've got here. Now we're using XUnit for our test framework for no particular reason. So we're going to load the accumulator with a value at memory location ix plus d when the operation is LDR ix. D is what we call the operation. Okay. So we're also using a mocking framework called Fake It Easy, or faking framework, whatever you want to call it. We're faking our bus. The bus only exists, as I've said, as an interface. There isn't any definition, a concrete implementation of iBus yet, because we don't really know what that's going to look like. But iBus basically contains a read and a write method. So we're reading from memory and writing to memory. We're assuming that the bus is a connection simply to a great big block of RAM at the moment. So there's no printers, there's no serial ports, no parallel ports, no video memory, no controllers like that on the bus. Simply, so we're dealing simply with reading and writing bytes to memory at the moment. Okay, what I'm defined here is a dictionary of a memory location and a byte, which is either an opcode or a piece of data. So this is basically our program that we're going to run as part of the test. We have every time we make a call to read, we're going to use this returns lazy feature of Fake It Easy to basically read whatever memory address we pass into the read method. ADR in this case, we're going to read whatever's at that location. So that's quite simple. We've also here create our CPU, and we're kind of preloading the registers. So we don't really want the H&L register, we want the IX register, and we're going to load that with 08FF, which is this location here. Okay, that's got an 8 in it currently. What we're going to do is, I think we're going to add a few more memory locations. So we'll have 2, 3, 4, 5, and 6, and we'll add some memory locations before it as well, because we want to be able to have offsets which are before the memory location held in register IX. So that's D, C, and B. So this is where IX is going to point to that location. We'll put zeros in these for now. So memory location 08FF contains the number 8. This is going to be DD, and then 7E I believe was our opcode. Let's just make sure it was 7E. Yeah, it is 7E to load the accumulator. Okay, so that's our kind of basic setup. We're going to read that. So the next byte is 0, so no offset whatsoever. So we'll say given displacement given D is 0. Okay, so we're not going to have any kind of offset, so we're going to read whatever is pointed to by the IX register, and that should be an 8, and load that into the accumulator. So we're going to test that our CPU A register at the end of the run, the first tick contains an 8, and we're also checking here that all of the flags are not set, because they start off unset. When we initialize our CPU, all the registers are unset. That's basically a test. It's going to fail. Can we run the test from here? And we should see a failure. We do. Okay, that's what we wanted. So this is red-green refactor. This is the TDD kind of cycle. It's 0, yeah. Boom boom. I like the handle. That's very good. Boom boom _4 underscores boom. Yeah, very good. Okay. So let's go over to our instruction and see what we do. So we can get the we can read our instruction here, and we should get that we're going to write into register A, which is what these three set bits here indicate. So we're kind of ANDing this, we're masking our opcode and putting out the value of these middle three bits, and we're shifting those to the right 3 bits. So again, we get a number between 0 and 7, and that's going to be our destination register. So you can see 7 is register A. So then we're going to read the next bit, the next byte rather, and that's going to be our displacement D, isn't it? Okay, so we're going to read the next byte, and our displacement is going to be that. So what is that going to be? It's a displacement. Okay, so a displacement can be plus or minus rather. Jabba, thank you very much for the follow. Have some electric elf. It's very kind of you to follow. Now to 86, 95.33% of our way to our target. So that's wonderful. Okay. So this is going to return a byte, but we don't want a byte for our displacement. We're going to want a signed byte here. So let's spell byte correctly. So we better, oh dear me, we better cast whatever comes back from there as a signed byte. This is the displacement, and it's going to be minus 128 through to 127 in its value. We'll put 2 plus. So this is how much we can offset the address that's held in IX from. So we can either go back from there 128 bytes, or we can go forward 127 bytes. It gives us quite a range of reach for the command. So now what we need to do is to combine that with the contents of the IX register, our index register. Oh yes, talking about the sports jersey, it's just come up on the stream there. Just pop over here into chatting for a second. This is the live coders team jersey that you've probably seen on Jeff's stream and other live coders. I'm wearing it for the first time on stream, so I'm really proud of it. So showing you off. Okay. So what happens next? So we need to combine that value with the contents of the IX register. So we'll save our address, absolute address in fact. It's going to equal. Yes, it does look good, doesn't it, Alka? It's really comfortable, and I was a bit worried because I ordered a particular size, not knowing about American sizing, but it actually fits perfectly. So I was really kind of pleased that it worked out. And big shout out to Lucky Number 11 for actually bringing these back over the pond, back to the UK, and posting them out. So if you don't know Lucky, then I'll give him a shout out. I think that's right. So he's a fellow live coder, and he's some really great streams, and a lot of Twitch extension development, which is quite fascinating stuff. So I do recommend his streams. Another UK-based streamer, actually doesn't live too far from me, which is we only just found out that we actually live quite close together. Okay, absolute address. So this is going to be the contents of IX, and then going to add D to that. So the code is very much reflecting the nature of the command. This is what I'm trying to aim at, that it's really quite obvious what's going on. So we grab the destination register here. We get a signed byte, which is the next thing we fetch in the immediate mode, and then the absolute address. I missed the equal sign. Yes, you're right. No, I haven't. That's okay. What did you say? Mr. K. I made him. Did I? Oh dear me. Let's try that again. If you're not a regular on my stream, you won't know that my typing is on stream. It's very, very bad. So let's just check. That's lucky this time. Keynote 11. There we go. Hopefully that's corrected it. Lucy. Yeah, let's call him Lucy from now on. Okay. So we now got an absolute address, and what we should be able to do now is say var n is equal to h1, and then we should be able to assign the value we get back to our destination. Let's use shader toy. Okay. So I think that makes a reasonable amount of sense as a piece of code, but let's test it. Okay, what do we get? A failure again. So what's it saying? It's saying that so 221 was not found. Dictionary. Oh, okay, I know what that is, so that's just a setup issue. Let's have a look. I think might need to step through because I'm not quite sure I understand why it's worried about that. So let's pop the current opcode. That's the problem. So root instruction doesn't contain the current opcode of. So what we need to do, I believe, is to drop this piece of code down into the else there. I think that is the best thing to do, at least initially. Let's just do a code cleanup on that. No, I don't believe that's what we should do. Let's put it back where it belongs. Okay, let's do the simplest thing that could possibly work for the moment. Let's put DD in as a no op in here. I'm going to copy no op actually, and I'll think about the best way of representing these extended codes, because they are codes in the table. So DD is a no op. I'll just put a comment, multi-byte code prefixes. I'll group them all down there. Okay, well that should sort that out. Okay, let's go back over to our test and try it again. Test. given key 0 was not in the dictionary. Okay, it's time to step through. So let's pop a breakpoint here and debug that test. And this, of course, is why we do tests. Let's see what happens. Okay, so we're going to step into the tick. Okay, so clock cycles is 0. We're going to read from the bus. Our current opcode should be DD, which is 221. Now we're going to increment the program counter. We're going to say if the code is DD, we're going to go into there. And you see we're using Coderush here, so we get this kind of true here, so we know we're going to go into here. You can see this part of the else is greyed out because we're not going to go in there. That's Coderush's visual debugging. That's going to give us a few clues of what's going on. Oh, we've incremented the program counter. That's the problem. We don't need to increment the program counter at that point. So let's try removing that command. Okay, so let's give that another go. Run the test. Did it run? Failed. Why is it not telling me why? That's interesting. It suddenly stopped behaving like it was just then. So debug Windows outputs. Oops. So what's it saying? Return value produced through an error. Given key 0 is not present in the dictionary. So that's the same problem we had before, so which is encouraging. At least we know it's the same issue. So let's drop that in there and run debug. Okay, step into tick. So we increment the so the current opcode is 126, which is good. 126 is 7E, is that correct? Get a programmer's calculator up. E. Good. So we're going to execute 7E. We're going to get the number of cycles back from that. That should be 19 clock cycles. We're going to step into that. So here we are in our method. So destination is register 7. That's correct. So now we should be reading and that's where we fall over. Interesting. That was supposed to be displacement D. Okay, let's have a look at what's going on there. So we're supposed to. Oh, we haven't loaded the correct value in. We haven't loaded IX into absolute address, have we? So thought I set it up as immediate mode. Let's go and have a look. Immediate mode, yeah. So immediate mode, addressing mode, immediate. The absolute address is increment program counter. Absolute address. That should have brought us back. The fetch one should have brought us back whatever was in the next byte from the program counter. Interesting, okay. But we want to know what the program counter is at this point, don't we, before we do the fetch. So let's say x equals pc. Just run this. Yeah, so Valerian, it's Coderush. I'm using Coderush, sorry, that gives the results, in that it kind of widens the lines between your code, and then pops some kind of help in there. You also get kind of a branch tree sometimes as well. It's really excellent extension. I really love it. So let's go over to test again. Step into there. So we know we've got the right opcode. Should be immediate mode. Step into there. So the program counter is 129. In our test. That's 81 or 81. And 81. So it hasn't incremented the program counter. Okay, that's good. So it's pointing at 81. And then our address mode says increment the program counter. Maybe we should pre-increment. We need to try that. Let's run our tests again. So we're still not, it's sending an address of 0 through, which is interesting. So why would it send an address of 0 through? So Coderush is more than just that. It has templating, all kinds of features in it. It's quite a comprehensive productivity tool, Valerian. So yeah, check it out. I'm expecting to get 0 back here, but it's reading, so it's fetch. So it should run addressing mode 1 at that point. Okay. This is what the tests are for. We'll into that. Step into here. $129, that was right, that's what we said last time. 129. Yep. Then we're going to step into this, and we're going to step inside fetch this time. So fetch should now execute addressing mode 1. Step into that. That's not addressing mode 1, is it? That's RDXHL. Okay, that's interesting. That's why it's not working. So over here, I'm pretty sure I set that to be immediate. Oh no, no. Yeah. Immediate mode. Why is it read the wrong? So 70, it would have been that addressing mode. So it's reading that addressing mode and not that addressing mode. So I've got, I think I know what it is. Okay, so the reason why it's doing it wrong is because in my addressing mode here, so my fetch, my fetch, it's reading that from root instructions. Okay, so we need to so fetch is going to need to be smarter, isn't it? So fetch is going to need to know about what table we're on. Are we on the direct, the DD, or the what's addressing mode? Angry Little Hamster. Fantastic handle, Angry Little Hamster. I'm sure have you been across on Coderush stream? I'm sure he mentioned an Angry Little Hamster. So the addressing mode is how we're going to get the data that we're interested in, and there are loads of different modes in the CPU. So the most obvious one is implicit. So there isn't any data to go and get. It's implicit within the command itself. So basically, do nothing at that point, which is IMP. Okay, implicit mode. Register mode is another one where the command itself tells you where to get the data from. But other commands, in this case, this is like an indirect addressing mode. It says, go to this address and get the data from there. And this is what this is. This is go to an address. If we go back to our addressing mode here, what we're trying to run is this immediate mode, saying go and get the very next byte contains the data. But what's happening is it's using, because these are the same opcodes from different lookup table, it's using this addressing mode. It's looking at the wrong table. You can see here it's using root instructions. So we kind of need to tell it so I think what we're going to do to get the test to pass, we're going to just create another one. This is not the solution. We're going to do the simplest thing we can to get the test to pass, and then we'll come back and do the refactor part of red green refactor. Okay. Let's just run it first and see if that actually addresses the issue. So we've still got a failure. Debug. Can't understand why I can't see my windows anymore, but it still says the given key not found. Interesting. Why is it? Okay, well, we just have to go through again. I think it's going to take a bit of thought. I think it's this. We set the absolute address, but we are in immediate mode, so we should. This is the problem. We need to use the fetch 2 now, I think. So we want to use the address. So this is why we've got fetch 1 and fetch 2. This is asking me to be fetch 2 DD, which is getting a bit messy, but we'll sort this out. Go over here. So rest assured, this is not how it's going to be in the end. And the addressing mode, the setting the addressing mode is not going to be immediate. So the first thing we look at it out of the next byte. So we make sure that's actually working first before we do anything else, so that we're getting the 0 back for displacement. Let's debug. Debug tests. So we're going to execute that. Oh, we've got a 0 this time, so that bit works. So now we need to use a different addressing method. Now we've got an absolute address here, which is going to be 2303 or 2303, and we need to go and get what's at that address. And that is going to be what's that going to be? It's going to be an addressing mode we haven't created yet, I believe. Okay. Stop. Go back to addressing modes. Okay, so it's going to be similar to an immediate extended. Given it an absolute address, so we've set absolute address over here in fetch, which is our messy kind of thing. Fetch DD. Okay, I think that this is what we need to do. We need to get rid of that as a concept, go over to instructions. Rather than doing a fetch, we actually want to read from bus ix plus d. Okay, I think that's... Well, I said it before, but we'll just try it out. Run test. And that's passed. You can see down here, 7 passed. Okay. So that's good. Just bring up the outputs. Windows, outputs, tests. Yep, 7 tests. Okay, so let's quickly just create a few more tests to test the displacement. So D is going to be positive. So here we're going to put in, so we've got 8 here. Let's go 1, 2, 3. Let's put 5 in there, and we're going to put 3 in our displacement. So we should get 5 this time, not 8. Get rid of this superfluous comment. That one. So let's bring the test runner over. Run those tests. Yep, so that passed. And let's do a negative value. At the moment all I'm doing is copying and pasting all these test methods. Obviously there's things we can do about refactoring this, but that's not quite the point at the moment. So here we have a negative, so we need to put a negative number in here, a negative binary number. This is what we call 2's complement, so we're going to put -1 in there. -1 is FF in 2's complement form, so we should put a value in the area, the one immediately before 08 FF, and we'll put it in here 15, and so that should take 15. And what we'll do is we'll in each of these we'll put 15 in here as well, so the program looks the same. 15. We're just picking different bits of data, and that was 5, wasn't it, in that point? Okay. Let's run those tests again. Build. Okay, so I think we can be quite happy that we've got our tests working. I think the thing to do after that is going to be to sort out this this fetch command. So the fetched command that we've got is currently a bit too dumb. We need to be able to tell it to look on different tables for the addressing modes. So currently what we're doing is just giving a completely separate command, but we need to pass an argument into the fetch command to say what table to look at. I think I'm going to tackle that next time. We're now at 6 o'clock and we're going for just over 2 hours. That's pretty much a good time for me on a Wednesday. Thank you so much for those of you who've joined the raid and stayed. That's very, very kind of you. Super duper thanks to those people who followed. It's been absolutely fantastic, so I'm really, really grateful. If you're still in chat and you haven't followed, can I ask you to follow, because it really helps me out, and I'm really shooting for this target of up here, the 180 and the 300. So there we're going on. Thank you for quoting Mark. Thank you so much. Have some electric elf hype. We're shooting for that 300 follower mark. So thanks very much. So my YouTube channel, where all my videos are archived, can be found here. Black Vulcan, fantastic name, wonderful. Thank you very much. Have some hyperspatial hype. these are all our alien buddy Alf, who's our kind of mascot, and it's getting to salute you all. So that's my YouTube channel. We've got about 65 episodes of Codebase Alpha up on there. So we do all kinds of things, all kinds of projects. We've created an Alexa skill. We've made a Microsoft chatbot, AI chatbot. We've done some GraphQL. We've done a bit of audio, dabbling in audio programming. We've got our shaders stream, which is proving really popular. So that's an ongoing series. We've also got our the bot, which we're developing. So our bot is quite an interesting one. We've got a launches command, and we're a bit of a space nut. So this, by default, the launches command will show you all the rockets that are due to launch by SpaceX. We also have an ask command, which is ask the bot anything you want. What is the Z80? And we'll see what it says when you ask what is the Z80. There we are. I think it's a Zilog Z80 CPU, so it does know about that. So we develop the bot sometimes. There's a text adventure we're working on, which is a long-term project. So on stream, we're gradually building the text adventure. It's quite a long way into development at the moment, and we're working on a troll at the moment, a literal troll that lives through a bridge and attacks the players. So there's that. All the archives for those are up on YouTube. It'd be great if you subscribe to me on YouTube. That really helps me out. Costs you nothing. Follow me on Twitter to have stream updates and when the next stream is going to happen. So that's my Twitter address. Yes, the Z80 is used on the Game Boy. Yes, so one of the things we could build once we've got an emulator that's working properly, we could build a Game Boy emulator. Yeah, we could play game. If I could play games, I could build you an emulator which played those Game Boy games. It may be something we do. Who knows? I've not got a fixed goal in mind for the emulator. It's a starting point and also something that I can put up on NuGet and people can use to build their own projects. I'm kind of leaning towards CPM running on my Windows laptop, so that should be quite interesting. GitHub, all my code is on GitHub. This is my GitHub. This code will be pushed directly after the stream. I'll probably do a bit of fiddling with this fetch command, but that's all up on there. So you're very welcome to go and grab any code from there. The Alexa skills up there. There's a JWT token enabled web API. There's all kinds of stuff up on there. So just go and view it. Let's go and find someone to raid, shall we? Because I think we're pretty much done. So once again, thank you for everyone who's followed. 288 followers, that's absolutely amazing. 96%, so just 4% of the way away from the target. So that's wonderful. I'm really, really grateful to you all. So let's go to Twitch TV and see who's around we can raid.
High analysis game because you guys
looks like Clarkio is available. Let's go and raid Clarkio, shall we? So if you haven't come across Clarkio before, he's a wonderful streamer. Clarkio is available. Let's go and raid Clarkio, shall we? So if you haven't been some video before, he's a wonderful streamer. Clarkio is available. Let's go and raid Clarkio, shall we? So if you haven't been some video before, he's a wonderful. Okay, so take care everyone and enjoy your day. Thank you everyone who viewed.